Hello, and welcome to Chapter 9 in Chem25. This chapter is going to be about energy, enthalpy, and in general we'll be talking about thermochemistry, one of my favorite subjects. So let's talk a little bit about energy. You've probably heard the term before, even if it wasn't very rigorously defined. If you've taken physics courses, for example, then definitely you did define a few forms of energy, as it's the most central of all quantities. And sometimes, energy is used in everyday context, such as, the energy in the food that we eat, okay? The energy that we need to live or work or play, and of course, when you're taking this course to study. Of course, some of the energy in the everyday context is referring to the energy that you need in your household, okay, or in the industry, or of course, very importantly, transportation, the energy that is coming from the various kinds of fuels, right, that go into your car or in the airplane and then makes them go. Where does this energy come from? And at the end of the chapter, we will discuss this. It can come from coal, it can come from oil, nuclear fuels, and then a more and more popular one, natural gas. And then we'll also talk a little bit about the so-called renewables. So what is energy? Well, the way the book defines energy is the capacity to do work or to produce heat. Now, of course, what is heat? Heat is energy transfer. So this is kind of a definition where a snake bites his own tail. And so a more precise and then physically correct definition would be a quantity, and I'm not going to read the whole thing here, a quantity that is somehow associated with time. In fact, the quantity that is the conservation of which is a direct consequence of a symmetry in time. What do I mean by that? Well, physical laws, right? The physical laws govern how, for example, if I let a ball drop, how it will, and with what acceleration it will go, how long it will take, all these various laws. Now, these laws are so-called symmetric to time. That is, if I do it today, or if I do it tomorrow, or if I do it a million years from now, it is still the same laws. Now, the gravity may be different depending on where I do it, but nevertheless, the laws are the same. And so in general, physical laws have this kind of a symmetry that is related to the time shift, right? And then you can actually fairly easily derive that there has to be a quantity that is conserved because of this, and then we call it energy. Okay, so the conservation of energy, the law of conservation of energy, is one of the most fundamental laws in nature. And it roughly says that energy can be converted from one form into another, but it can never be created or destroyed. So the total energy quantity of the universe is constant. It does not change. And this is very important because in the next chapter, we'll be going to a different quantity called entropy. And then entropy is a very different fundamental law associated with it, that it will always have to increase, okay, rather than just being conserved like energy. Okay. Now, what kind of forms of energy are there that we need to know about? Well, the two forms are potential energy, and the potential energy is due to a position or a composition, which is just a fancy form of a position. What do I mean by that? Well, for example, if you have water behind a dam, okay, then depending on how high that water level is, it stores more and more of this gravitational energy. But how does this relate to chemistry? Well, if you go down to the very, 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 very tiny level, to the level of atoms, and then even beyond, then you can see that the distances of the electrons from the nuclei to another, one nucleus to another nucleus, or the other nuclei in general, these distances are a form of potential energy as well. And so these attractive forces that exist between these elementary particles, they will govern how much energy is stored in these molecules. And so the differences between the attractive forces in a reactant or a product that is directly related to the chemical energy or the energy that is either liberated or absorbed during a reaction. And we'll spend some time at the end of the chapter talking about this aspect of energy. And so potential energy is one of the forms that we have to know about. What is the other one? Well, the other one is kinetic energy, right? The kinetic energy is directly related to the motion of the object. Okay, so the faster it goes, the more kinetic energy it stores. And in fact, it's important to know the actual functional form, and it scales with the square of the velocity. Now, this means that if you accelerate from 0 to 60, okay, and then from 60 to 120 miles per hour, that's probably a wrong example. I watch too much Top Gear, I guess. Then the energy doesn't increase twofold as your velocity did, but it increases fourfold, okay, because it scales with the square of the velocity. It also directly scales with the mass. And so objects that have the same velocity, but one is heavier than the other, will just carry more kinetic energy. And this is, of course, very important. That's why a lot of people buy SUVs and then spend a lot more money on fuel, because the car is simply heavier, and then it takes more energy to accelerate at the same velocity, but it also stores more kinetic energy with it. So when it hits other cars, then there's less damage to them and not the other car, of course. But can these various forms of energy be converted into one another? Well, it should be, because what we said is the total energy that is conserved. And so if we have some amount of potential energy, we can convert it to kinetic energy, and then we can convert it back. Okay, so a simple example for that would be, you have a ball here held in place, and you let it go, and the ball rolls to position B. And the kinetic energy, obviously, is higher in point B, because now it's rolling in this direction. But at the same time, the potential energy decreased, because in a gravitational field, it was here, and then it went down there. And so we have converted potential to kinetic energy. Okay. Or actually, well, what this meant was that I have two balls. Okay, so let me have a different explanation. So I had a ball A, okay, which is held here in a potential energy that is higher because of gravity, and then it rolls down, it actually hits ball B, and then ball B will roll upwards, okay? So what happens is that the potential energy of ball A will be converted first to its kinetic energy, then the kinetic energy of ball A, when it hits, it's not pictured here, then it's converted to the kinetic energy of B, and B starts rolling, and then it will in the end turn into the kinetic potential energy of B, because it's sitting higher. Now you can also maybe tell that the original position of the ball A was here, and then the ball B is lower than that. So does this mean that we have lost some of the energy? Well, I said earlier that energy is conserved, so probably not that. Well, what happened is that there's probably also some friction, and when this rolling happened, then some of that friction caused the energy to be lost, and then, well, it's hard to measure, but it will be manifested in heating up slightly over over this course, both the hill and the balls, because of the friction. Okay, so how can energy be transferred? And so this is the important part. How is it transferred between objects? And so we will be talking about two ways: heat and then work. Heat is an extensive property, which means that if you double the size of the system, okay, then the heat will double with it. Okay, so let's say if I have one brick at a certain temperature, and then how much energy it transfers when it cools down. If I had two bricks, then the heat will scale accordingly. Okay, temperature is not the same, right? Temperature is an intensive property, which means that if I have one brick at 30 degrees, if I have now two bricks, it's not going to be at 60 degrees, but it's staying 30 degrees. Okay, if I have two rooms, and when I open the door in between, the amount of energy stored in the room will double, if the sizes are the same, of course, but the temperature will not double, but it will average between the rooms. So the temperature, as we've already seen in chapter 5, is somehow related to the random motions of the particles. Okay, so the faster they move, it represents a higher temperature. Of course, this is average velocities. Remember those distributions we talked about in chapter 5. But anyways, heat is an extensive property, and it refers to the transfer of energy between objects due to a temperature difference. And so, for example, carrying on this discussion of bricks, if you have a cold brick and then you put on top a hot brick, then the hot brick will lose some of its stored energy, and then in the form of heat, it will go into the cold rock. Now, nothing macroscopic is moving, so we're not talking about one brick doing work on the other brick, but it's simply the energy transfer that is due to temperature difference. However, on the other hand, work is a force that is acting over a distance. And so if I went back to those balls that I was talking about, and I acted with a force on one of them, I could move it from an initial position to a higher one, right? I put in work. And then if you calculated how much force I was using over what distance, that would give you the energy difference. That is now the work that I exerted. And so, again, what we can do is we can take work, put in work into the system, and then cause, let's say, a change in the potential energy. Or in kinetic energy too, I can act with a force over a distance and make the ball roll faster, thereby putting in more kinetic energy, right? So I can increase either its potential or kinetic energy. There are two ways then to transfer energy. We can do it through work, okay, or we can do it through heat, okay. Again, work is by exerting a force over a distance, and heat because of a change in temperature or a difference in temperature. And now let's discuss what ways a system can go from point A, a certain configuration, to point B. We call them pathways. Okay, so for example, if you remember those balls, when you take ball A and it rolls to the bottom of the hill, then no matter how it does it, okay, it will always lose the same amount of potential energy. Okay, then what happens first is most of it is going to be its kinetic energy, and then ultimately it will end up as a potential energy of ball B. Some of the energy is of course lost because of frictional heating, okay, depending on how the hill looks like. But regardless of the conditions, the total energy transferred is always constant. Okay, how much is transferred into heat and how much will go into work differs between different pathways, but there's some which is the change in energy, right? That is always going to be the same. The change in energy of ball A and then the ball B and then the hills together will always have to be zero because energy is conserved. And so the energy change is independent of the pathway, but how much is due to work and how much is due to heat are dependent on the pathway. But when you add them up, then they become independent. And that's a very important point. Then we will have a system in a certain condition and then change it in a different condition. And then we can do it various ways. First increasing its pressure, then changing its volume, or manipulating the temperature. But if we're going from point A to point B, then no matter which way you're going, the total energy change is going to be the same, but it will not be the same for work and heat. And so those quantities that are independent of the pathway, we call them state functions. Why state function? It's not the kind of state function, that politicians go to, let's say Richard Nixon in this case, but it refers to a property that only depends on the state, its present state of the system, and it does not depend on its past, how it got there, how it arrived to the present state. It does not depend on any of these, but only on its present state. Okay. And so Another way, in terms of pathways, it doesn't matter what particular pathway we're taking, it's independent of that, and it's only going to be dependent on where you are. Okay, energy, for example, is a state function. Okay, no matter how you got there, if you define what state the system is in, you can calculate its internal energy, but the work and then the heat that are associated with changes in the system do depend on which pathway you're taking. And obviously this is a chemistry course, right? And so we'll be talking a lot about the energy changes that are associated, that are happening when a chemical reaction is going on. And of course, a very typical one would be the combustion of methane, which you take CH4, and with O2 you turn it into CO2 and water, and very importantly, into excess energy that is coming out of the system. Now, I said system. What does system mean? Well, from now on, the system for us will mean, the system is defined as the part of the universe on which we are focusing our attention. Okay, so if we are talking about the combustion of methane with oxygen into CO2 and water, then the system will be all these chemicals together, reactants and products. And then what is the rest? Well, the surroundings are everything else in the universe, all right? So surrounding is not just what immediately surrounds it, but technically anything that is not the system, which would be universe minus the system, we call the surroundings. And in this case, of course, that will be reaction container, the room, if you're using methane, for example, for heating, or in general, everything else. So we'll distinguish between system and surroundings, and we'll talk about which way the energy flows from systems to surroundings or surroundings to the system. And so if you have an exothermic reaction, exothermic means, exo means out, okay, it will result in the evolution of heat, and energy through heat flows out of the system. Okay, the important part is it flows out of the system, from the system into the surroundings. And the opposite of that would be endothermic reaction. Endothermic means endo is going inside. Okay, so when a system absorbs energy from the surroundings and heat flows into the system. Okay, so exo, out of the system, endo, into the system. Okay, if you ever forget it, think of, for example, exoplanets, right? Exoplanets are outside of our solar system. Now, can you give an example for an exothermic reaction? Of course, this one here. Typically, combustion reactions are exothermic. If you use natural gas or methane, right, this guy here, when you're cooking something on your stove, right? If your house is hooked up to the natural gas line, or you probably use this for heating as well, right? And again, these are exothermic processes, these combustion processes. Or you can buy a tank of propane at Home Depot and then take it home and then grill a burger in the backyard, again, by using the heat that is liberated, this heat that is liberated in this combustion process. Now, what about a reaction that is endothermic? Well, an endothermic reaction could be, for example, this one. When you're mixing N2 and O2 at very high temperatures you need for this, let's say this happens in a jet engine, typically, or to a smaller quantity in diesel engines too. Essentially taking nitrogen and oxygen, rip up the bonds between two identical atoms and turn them into nitrogen monoxide, which of course is actually fairly toxic and it's a pollutant, but nevertheless you need energy put in, right? So you have to put in extra energy for this reaction to happen. And you can say that, remember the ball? If the ball was rolling down, then energy was coming out of it, and then maybe it was given to another ball, ball B. However, if I put in energy in the form of, let's say, work, I could put the ball back into a higher energy state. That way, its gravitational energy increased. Now, what about the energy of reactions? So what this means here is that the reactants, okay, so the N2 plus O2, and it goes into the product NO, then it needs to absorb energy. So somehow this is on higher ground than the reactants. You have to push it up a hill to make it into nitrogen monoxide, and that's actually a very good way to picture it. So Let's talk about exothermic reactions first. Where does that energy come from? Okay, as I mentioned, you can use the analogy of a hill. And so if energy is coming out of it, it seems like the chemicals that take up the reaction, the reactants and products, they will roll down to lower energy state. And so the difference in the potential energy between the products and the reactants, that's where that heat is coming from. The total energy is conserved, okay? But when energy flows from the system into the surroundings, then that energy gained by the surroundings is the same as the energy lost by the system by the product or in a lower energy, that is more stable state than the reactants. And so when you take again the combustion of natural gas methane, the energy content of the chemicals decreases. That is, 1 mole of CO2 and 2 moles of water has less potential energy. They're lower in chemical energy than 1 mole of CH4, methane, and 2 moles of O2 molecules. So overall, these chemicals have stabilized. They're in a lower energy state, and that energy difference went into the surroundings, and we use it, for example, to heat up something on the stove or heat our house or any of that. And so when heat flows into the surroundings, it comes from by lowering the potential energy of the reaction system. Okay. Now, how to put it in a different way, focusing on the bonds. So the chemical bonds that are in the products, okay, are more stable than the bonds that are in the reactants. And so when you're breaking up the bonds in methane and O2, and then form new bonds in CO2 and water, those new bonds will be more stable, and therefore they're in lower energy state, and that the difference is converted to the thermal energy via heat, and then it leaves the system, goes into the surroundings. And so let's visualize these changes. So when we talk about the chemical energy of the system, then the change in this potential energy is the difference between the energy that you require to break the bonds in the reactants, and then you release the energy when bonds are formed in the product. And then depending on which one is more stable, you can have an exothermic or an endothermic reaction. So exothermic reaction, and the products are stronger, okay? So when you go from O2 and methane, you need 2 moles of O2 for 1 mole of methane. The energy is lowered for the system when it goes to water and CO2. So you can say that water and CO2 are more stable chemicals. They're in a lower energy state. They have stronger bonds between them. And so the chemical energy of the system is lowered. At the same time, this energy difference is not lost, of course, because, energy is always conserved, but it released to the surroundings as heat. Now, how does it look like for an endothermic reaction? In an endothermic process, you have the opposite. The bonds in the reactants, let's say in N2 and O2, are stronger. So when it goes to NO molecules, nitrogen monoxide, you have to put in some extra energy, and that is coming from heat entering the system. Heat is absorbed by the system, and that can raise the chemical energy from N2 and O2 onto the less stable nitrogen monoxide molecule. Okay, so now we kind of understand how this works. What is the sign, okay, for the heat flow in an exothermic and the endothermic process. So let's just quickly summarize it here. So when you have an exothermic process, okay, from the system, heat goes into the surroundings, okay, and so from the system's perspective, the heat, the Q, is negative, okay, so the heat is less than 0, it's negative. Heat is flowing into the surroundings. When you look at an endothermic process, then heat flows from the surroundings into the system, and from the system's perspective, the heat flow is positive. It's absorbing heat. Okay, so This leads us to the main topic of this chapter, thermodynamics. So thermodynamics in general is the study of energy and its interconversions. And the very first law that we've already formulated slightly differently, but it's essentially just that the energy is conserved, or in other words, the energy of the universe is constant. Okay, so if you have any process whatsoever, the total energy of the universe cannot change. But of course, how much is in the system versus the surrounding, that can change. And so we will be talking about the internal energy of the system, and we'll use the letter E, which is the sum of all kinetic and potential energies in the system of all the particles. Okay, you can change this total amount of internal energy through work or heat, or you can do both. Okay, you can act with a work on the system, or the system can do work. Heat can enter the system, energy can enter the system through heat, or the system can lose energy through heat, and that can go into the surroundings. But in general, the total energy change, which we will denote with a delta E, is the sum of these two, the heat plus the work. So this is the most important formula. If you only remember one formula from the entire chapter, I hope it's not the case, but it has to be this one, right? That the total energy change in the system can come from two sources. It can come from heat and then from work, and it's the sum of these two. And again, remember that heat and work are not state functions. And so depending on what pathway you take, if you go from point A to point B represented in the state of the system, and this is one pathway and this is another pathway, the individual contributions of the heat and the work will be different, or can be different, but the total energy change has to be the same. And so in general, when we talk about thermodynamics, then the quantities involved will very importantly have two parts. Okay, it will have how much is the change, right? How much work, how much heat is involved. And then also the sign will be direction of the flow, always from the system's perspective. Okay, and so the sign of this energy change, as I already mentioned briefly, and then this is the take-home message here, is that from the system to the surroundings, if energy flows out, then the energy change is negative from the system's perspective. If it flows in from the surroundings into the system, then the energy change is going to be positive. And so that is true for heat, as we already said, that if the energy flow is through heat, then if the Q is positive, then we're talking about an endothermic reaction and the system's energy is increasing, or energy flowing out of the system, then the Q is negative and the system's energy is decreasing. Okay, so this is what the sign means. The absolute number will tell how much, but the sign will tell you from the perspective of the system, and that is true for work as well. And this is important because that's kind of a little bit counterintuitive, especially if you're an engineer. So the same conversion applies here, that you define work, okay, from the perspective of the system, which means that if the system loses energy through work, then the work is negative. What does it mean loses energy through work? Well, if the system does the work on the surroundings, okay, then energy flows out of the system and then the W is negative. So for example, if the system is a mixture of chemicals inside a cylinder, and then it pushes the piston out, okay, against the outside force of the atmosphere, then the system is doing work, and from the system's perspective, it's negative. Okay, so in general, when there's useful work involved, from the system's perspective, we're talking about a negative work. Okay, energy flows into the system, right? So switching to the other side, if the work, however, is positive, means that it's not the system doing work, but the surroundings do work on the system, and then energy flows into the system that way. Now, just know that this convention is not always followed everywhere, right? And so sometimes mechanical engineers define the work from the perspective of the surroundings, simply because what you're talking about is, can I do useful work, right? But in chemistry, the convention is always from the system's perspective. Again, if the system is doing work, right, then the work is negative. And if the surroundings do the work, then the work is positive. Okay, just like with heat. And so therefore the two can be added together and they represent the total energy change here. Now, what kind of a work can we talk about? And I already mentioned that, okay, what about if you have some chemicals, let's say some hydrocarbon that is blowing up inside a cylinder and it's pushing the piston. And a good example for that would be this Ferrari engine here. I'm not sure what those red things are on top. Maybe are those the turbochargers? I'm not sure. Anyways, a common type of work in a chemical process is what we call the pressure volume work. Okay, that is we're doing work either by a gas or to a gas. If the gas expands, then the gas is doing work. If something is compressing the gas, then work is done on the gas or to a gas. Okay, and so that reaction that I mentioned, that the heat that is from a combustion engine using gasoline expands the gases in the cylinder and the piston is pushed back, and that essentially in the end ends up as the motion of the car, right? And so the system is doing work, and that work is used by this engine to drive the car. And so let's do the math here. If we have an initial state that is going to this final state, and then which represents an expansion, how much work is there in this case, right? How can we calculate this amount of work? Because essentially, remember, work is force over a distance. And so if we know the force here, of course, which is related to the pressure, it's force over area is the pressure. And so the force that the gas acts upon is pressure times the area. Then we can calculate how much force was involved. Okay, at the same time, right? Remember, it's force over a distance, and so the distance will be this delta H here, right, from the initial to the final state, and that will be associated with a change in the volume, right? Because delta H, right, times the area here will give you the volume, that is the volume change of the gas from the initial to the final state. So when we do the calculations, the magnitude of the work, remember we'll come back to the sign in a moment, the magnitude of the work is simply the force over the distance, right? So F times delta H was the distance that the piston was going through. And remember that the pressure is force over area. We first came up with this in chapter 5. And so if you take the force and we multiply it with the delta H, the force is pressure times the area. And then when you multiply it with the delta H, area times delta H, as I showed you on the previous slide, is essentially the change in the volume. And so overall the work is pressure times area times the distance, and that happens to be pressure times the change in the volume. So this is actually very convenient. And of course, if we're talking about the SI, which also means that if you take pressure and the SI unit for that is Pascal, and then multiply it with the change in the volume, which is measured in cubic meters, which is Pascal times cubic meters, gives you joules, which of course is the unit for energy. Now, again, what about the sign? Remember, in thermodynamics, we always have to talk about the magnitude, right? The magnitude, what's given here, it's pressure times the volume change. But what about the sign? If the gas and the system is moving the piston against an external pressure, then it's a system that is doing work on the surroundings. And so if, and this is important, if this delta V is positive, okay, that is, the system's volume increases because it's doing work on the surroundings, it's expanding. If it is positive, then P times delta V is positive, you know, pressure is positive. And so we have to put in a negative sign to reflect that the system was doing work, and then the work is going to be negative, right? So the final formula is work equals minus, and don't forget the minus sign is very, very important, minus pressure times the volume change. So let's do a calculation. Okay, what if we have a balloon, and then the balloon is inflated by heating, the air inside it. And so let's say in a certain stage of this process, the volume changes from 4 times 10 to the 6 liters, which would be 4,000 cubic meters, to 4.5 times 10 to the 6 liters, which would be 4,500 cubic meters. And at the same time, you're adding this much energy as heat. Okay, so 1.3 times 10 to the 8 joules, or 130 megajoules of energy as heat. And let's say if we assume that the expansion is against a constant pressure, right? And that constant pressure is the pressure of the atmosphere. In this case, let it be 1.0 atmosphere. What will be the energy change in the process? And remember, the energy change is Q plus W, right? So we have to calculate the W from here, right? What is the volume change against what is the outside pressure? And then the Q is given, right? Addition, which means this is going to be a positive quantity. What about the work? Well, the system is expanding, right? So it's minus P delta V, so that is going to be negative. And when you add it up, you should get the energy change. Okay, so I deleted the image so that we can do the calculation. So how would this go? Well, first of all, again, let's write it down that the delta E equals Q plus W. And the Q was postulated as 1.3 times 10 to the 8 joules, okay? That was the heat that is given to the system. And again, it's an addition, so the Q is positive. And then the balloon expanded against a constant pressure of 1.0 atmosphere. So it's minus P delta V, which is minus pressure. And then let me just write down everything in the units that were given. So 1.0 atmospheres, okay, times. And then we look at the volume change, which is from 4.0 to 4.5 times 10 to the 6 liters. And so, well, let's write everything out just this time. Times 10 to the 6 liters minus 4.00 times 10 to the 6 liters, right? And so this is 5.0 times 10 to the 5 liters is the difference between the two. And so what do you get? You get minus 1.0 times 5 times 10 to the 5th. So that would be minus 5.0 times 10 to the 5th liter atmospheres. Ooh, liter atmospheres. Okay, that's not a terribly useful unit, isn't it? So since the first one was given in joules, it would make sense to convert it to joules. And so how many joules is 1 liter atmosphere? And so for that, let's take a side note. I think, oopsie, I've shown you this probably in chapter 5 already, but just let's revisit. Okay, so 1 liter, okay, is 10 to the negative 3 cubic meters. So between liter and then the SI unit, okay? And then 1 atmosphere is 101,325 pascals. So hopefully you memorized that number. It's very close to, a bar, but it's slightly more. And so if you multiply the two, then 1 liter atmosphere. And then what will the unit on the right? Remember, and that's the power of the SI system, that SI times SI is SI. And so if you multiply cubic meter with Pascal, you have to get the SI unit, which just happens to be joule. And write 10 to the negative 3 times that large number will just end up being, my handwriting is beautiful, so it's 101.325 joules for each 1 liter atmosphere. And so let's multiply this with 101.325 joules over 1 liter atmosphere. And if you do that, let me get my calculator here. And then let's do this. So negative 5 times 10 to the 5th times 101.325, and what you get is minus 5.066. So I know already that it's going to be rounded around there. So 5.1 times 10 to the 7th joules. Okay, and so what is the delta E? The delta E equals Q plus W. The Q was given here. We calculated the W. And so if I add that 1.3 times 10 to the 8th to this, then what I get is 7.933. But where's the last significant figure? It was in the 10 to the 7th. Okay, so you get 8 times 10 to the 7th joules, and it is positive, right? Which means that the heat that entered the system was bigger than the work that left the system, and so the absolute value of the heat was larger than the absolute value of the work, and therefore the net change was positive. Now, does it make sense? Where does the internal energy change of the system come from? Well, it's coming from heat and then work. But how is it manifested? It's manifested by the system having in a higher energy state, its molecules running faster, having higher velocity, having higher kinetic energy. What does it mean? Yes, it is at higher temperatures, which of course makes sense because you're inflating this balloon by heating the air in it. And so that heating is manifested in this energy change. And then some of that was used to do work against the surroundings, right? So this was a simple PV calculation, but it leads us to a different quantity because, and why do we need this? Well, first of all, most of the processes we're interested in are carried out at constant pressure, right? What do I mean by that? Well, if you have an open vessel in the lab, let's say a test tube or a flask, then when you're heating it, when you're doing chemical reactions, the outside pressure is the same. It's that 1 atmospheric pressure. Okay, so the pressure is typically constant, and then the volume of the system can change. And so even though, let's say, a certain amount of energy change is associated with with a chemical reaction, let's say, or some physical process, that is not terribly relevant to us because you also have to take into account, okay, but at the same time, the system was doing work. So we can have to subtract that to get how much heat is involved. And so we can just put this into the quantity that we're interested in. And from now on, instead of talking about energy, we'll be talking about an associated quantity, which we'll call enthalpy. Now, fortunately, this sounds kind of, okay, why do we need this, right? And wasn't energy enough already? Well, the thing is, it just simply automatically builds into it, right, the energy change that is associated with the pressure volume work. And so if you add this PV quantity into it, then from now on we'll be talking about enthalpy, and enthalpy will be the one that is directly associated with, how much heat is liberated or absorbed in a process if we're talking about processes at constant pressure. Okay, so what you need to remember here is that the way the enthalpy is defined is H equals the energy plus P times V. Okay, now the pressure, okay, the volume, and the internal energy, they're all state functions. That is, they do not depend on the pathway the system took. It only depends on how it got there, which is kind of course, trivial for pressure, right? The pressure is the pressure in current state. The volume doesn't matter which way you decrease the volume and then increase the volume, or increase it to much larger and then decrease it a little bit, or just did it all in one step. The volume is the volume. And we've already seen that energy is a state function. So when you put these three together, that has to be a state function as well. And so enthalpy is a state function. Don't forget that. Okay, this is going to be extremely important later in the chapter when we get to my favorite part associated with Hess's law. And so let's say you consider a reaction that is at a constant pressure. And so the change in energy, we already said that, it's coming from Q plus W, right? The heat plus the work. Now, what is the work? The work is the pressure volume work, which is pressure times the volume change, okay? And remember that it was negative. Why? Because if the volume increased, then the system was doing the work and therefore it had to be negative. So the delta E equals Q minus P delta V. What about the change in the enthalpy? The change in the enthalpy, delta H, is the delta E plus the change in the pressure volume work. And let's write this down so that we know what we're talking about. So the delta in the PV, okay, it can come from change in the pressure, change in volume, or both. But remember, we're talking about constant pressure. And so we can bring the pressure out from the delta, and then we get P times delta V, which happens to be, thus the pressure volume work. Minus the pressure volume work, actually. So the delta H is delta E plus P delta V, right, which came from the delta in the PV. And so since this was the pressure volume work, this simply comes down to the delta H, right, equals, remember, put this over there, is simply the heat. And that's why we brought this in. That's why we ended up defining this enthalpy quantity, because the change in the enthalpy, if we're doing a reaction at constant pressure, is going to be directly the heat that is associated with the process. Okay, and so for processes at constant pressure, the change in the enthalpy is equal to the flow as heat. Okay, so the heat flow, and so the heat flow is essentially a measure of the enthalpy change of the system, and therefore we actually use them interchangeably. When we talk about enthalpy change, sometimes we just call it heat. So in fact, that's what we do. This is actually my research area. We carry out a certain kind of complicated experiment with the purpose, oftentimes, to determine enthalpy changes, but we don't call them enthalpy change, we call them heat, right? And then we talk about the heat of a reaction or heat of formation when you're creating a certain compound from its elements. And so heat and enthalpy change are interchangeably used because at constant pressure, and that's what we're mostly interested in, the two represent the same quantity. Okay, so again, the change in the enthalpy, what is this R doing here? Just referring to change upon a reaction, which is, the product's enthalpy minus the reactant's enthalpy. That enthalpy change, sometimes we call it the heat of this reaction. Okay, now, what about the sign of it? Again, if the products have greater enthalpy, higher entropy, then the delta H is positive. The heat is absorbed by the system, and we're talking about an endothermic process. So in an endothermic process, the delta H or the Q is positive. However, the reactants have greater enthalpy, so it's a downhill process. Then the delta H is negative, and we're talking about an exothermic process because heat is generated by the system and it's leaving the system, from the system going to the surroundings. Okay, very nice. So this leads us to maybe a bit more in-depth investigation and how this looks like for an ideal gas, how this is associated with temperature and then changes in temperature. So, and then, by the way, at a lower level, you probably saw this in a prerequisite course, let's say CHEM25, or if you took an AP class in chemistry in high school. And so remember from chapter 5 that the average kinetic energy of the gas molecules is 3/2 RT, and I'm talking about an ideal gas and ideal monatomic gas. Okay, and we're not talking about let's say diatomic and its vibrations in there or the rotations, but let's say you just have an ideal gas made of atoms. Then the average kinetic energy of these gas atoms is going to be 3/2 RT. And then also remember that this is coming from the fact that we live in a three-dimensional space, which means that each independent direction X, Y, and Z can store 1/2 RT of energy. And so if you change the temperature of an ideal gas, then the kinetic energy of the particles will change. And then the change is simply, it's on average is 3/2 RT. If you change the temperature by delta T, then the energy will have to change by 3/2 R delta T. And we can call this, the heat capacity, right? How much energy is required to raise the temperature of a certain amount of a substance. Let's call it 1 mole by 1 Kelvin, right? And then if you multiply this, then this is how much heat, how much energy is required. And let's call it molar, because we're talking about 1 mole, and then heat capacity, how much you have to put in for a certain temperature change. Now, this 3/2 R, which you multiply the delta T with, is then the molar heat capacity for an ideal gas, okay? So again, this is for a monatomic ideal gas, and this 3/2 R means that if you're heating up the system by 1 degree and you have 1 mole of it, then each degree of freedom, X, Y, and Z directional motion will each store 1/2 R. Okay. Let's go one step further. Okay, what about the PV work? Remember that sometimes when we did some change in the system, let's say what was chemical, or in this case just purely thermodynamics, sometimes the volume changed and there was a work associated with it. So let's first focus on the simpler one. What if the ideal gas that we're talking about, it was heated at constant volume? Okay, which means that we used a rigid container, right? The walls didn't change, and therefore the volume didn't change, and so the delta V equals 0. Therefore, there's no PV work, right? P times delta V minus P times delta V equals 0. And so this also means that since the system was not doing work, then all that energy that flows into the gas is used to increase the transition energy, or the temperature of the gas molecules. And the molar heat capacity is simply the amount that is needed for that and just that, and no work involved. And the molar heat capacity is 3/2 R. Okay, and so molar heat capacity when the V equals constant, that is rigid container, no volume change, then it's going to be 3/2 R. What about constant pressure? And again, this is the more useful part, because most of the reactions, let's face it, will carry out at constant pressure, and the size of the container can change. And in this case, the volume does increase, and so PV work does occur. You supply energy for two purposes now. You change the transition energy to gas, that is, in layman's term, increase the temperature, right? But at the same time, also the work is doing the gas is doing some work, okay? Because the gas expands, and therefore it does work on the surroundings. Remember, the ideal gas law PV equals nRT. Right, and then what is changing here? The pressure is constant, so we can bring this out. So the P times delta V equals, and then the R, of course, they don't change, the amount of mole of a gas, and then the R is, of course, a constant. And so it's nR times the delta T. And so what does it mean? That if the delta T is 1 Kelvin, you have 1 moles, then the PV work that is associated with it is simply R. So this means that when you're putting energy into the system, and this is important, okay, remember we used that 3/2 R that was associated with heating up the system, making the molecules go faster. But again, we have to put an additional R, which will be reflected in the work that the system does at the expense, okay? Because a delta T, right, a change in the delta T will be associated with the delta V from the ideal gas law. And so this, if you put those two together, then it means that the CP for a monatomic ideal gas is 3/2 R plus R, which means 5/2 R. Or you can also say that the CP is CV plus the additional R that is associated with the pressure volume work. Now, what about a polyatomic gas? Because we talked about, ideal gases, but for us, an ideal gas didn't inherently mean that it was also monatomic, right? It can have an internal structure. Let's say if you look at oxygen, and then low enough pressures and high enough temperatures, it does work like an ideal gas. If you carry out experiments on it, then it does fulfill the PV equals nRT. So nothing says that an ideal gas cannot be polyatomic. But that value that we just derived for the CV assume that it consists only with particles with no structure. Remember the kinetic theory of gases? That's what we assumed. It was just balls going around, and the only change in energy was associated with their translation. But if the particles are monatomic, then there's other ways to put energy into them. Okay, so first of all, if the particles are monatomic, then the CV is actually very close to 3/2 R, means they do work, they do behave ideally. But if you look at a polyatomic molecule, then the CV can be much greater than 3/2 R, because there's other ways to put in energy. So for example, if you look at SO2, sulfur dioxide, then it's actually, if you measure it, it's around 4 Rs. How much is that? Well, 3/2 R are associated with translation. Let's assume that another 3/2 are associated with rotation. Why is that? Well, just remember that if you can move in 3 dimensions, it also means you can rotate in 3 dimensions. That is, it can rotate around an x-axis, y-axis, and z-axis independently. And you can assume that now we have 6/2 or 3 Rs that are for the translation and rotational degrees of freedom. But there's more, because you can also start vibrating that molecule, right? The SO distance or the OSO bond angle can change, right? The molecules, let's say, I'm trying to show this, it can do that, right? And that is associated with some internal energy as well. And so overall, you need to put in not 3/2 R, not even 6/2 R, but 4 R for accounting for these various degrees of freedom. But important that this elevated value, this higher value of the CV, is not because of non-ideal behavior. It can be still a perfectly ideal gas. Let's say for SO2 at high temperatures, pretty ideal, right? So it's not because it doesn't obey the ideal gas law. It does. It's just simply because the molecules can absorb energy in different ways, more than just a translation of motion. It can also have rotational and vibrational motions inside the molecule, right? It's kind of important. And there are some molar heat capacities of various gases, the CV values here and the CP values there, and you can see that lowest is for monatomics, helium, neon, argon, very close to the values we derived. And then what about the difference? Well, the difference is at 8.33, which is of course the R. Okay, it's 8.31 in SI units, so it's very close to that. And if you look at different other gases that behave mostly ideally, then you can see that even though the CV is a fair bit higher. Now, how much higher? It's actually interesting to see. Can you roughly calculate the difference between these two values? If we say that a monatomic ideal gas is 3/2 R for the CV, how about the hydrogen? If it's still ideal and everything, how many more extra degrees of freedom? It looks like it's around 8, right? Which is 2/3 of the original value of 12. It means that this change is around an extra R. And remember, an extra R is 2/2, right? And so 2 degrees of freedom. What do you think this means? Well, it means that the hydrogen molecule is like a stick. It can rotate, but it can only rotate in 2 dimensions, not 3, right? Because the third rotation would be along the axis, so it doesn't make any sense. And so it looks like it has 5 R's, 5/2 of R, right? 5 degrees of freedom, which of course makes total sense. 3 translations and then 2 rotations. But another thing that you can look at is, what about the difference to the CP? And the difference still happens to be this 8.3, which is 1 R, right? So no matter what we do, when we go from CV to CP, we add in that additional R, which was associated for an ideal gas, again, with the pressure volume work. Very nice, very nice. This is a logical subject, right? Okay, and so let's go back to how the energy change is upon these processes. So if you change the temperature, right, that's how change the energy, the internal energy of ideal gas. And so the delta E is going to be this, let's say C Well, okay, the CV, okay, 3/2 R times the delta T, and so the delta E is N times CV times delta T. Now, what about the heat? Okay, so the heat is not the same as the energy change. Remember, work is involved as well. So at a constant pressure, it's N times Cp times delta T, okay, which you can write out as the Cv plus the additional R. Remember, that separates the Cp from the Cv. And if you dissolve the parenthesis, then you have the N times Cv times delta T, and the Nr delta T. 1 is then corresponding to the energy change, right? And then the rest is going to be the negative of the work. But nevertheless, if you carry out this process at constant temperature, the delta E is just associated with raising the temperature, okay? And the heat is taken into account then how much was used for work at the same time. Okay, so we're done with energy. What about the enthalpy? That's also quite interesting, right? Because the enthalpy change is the energy change, okay? Because enthalpy is energy plus PV, plus the change in the PV. And so from the ideal gas law, remember the change in the PV would be the change in the nRT, right? Because PV equals nRT, so the change in this one will be the change in that one as well. So you can put in the delta in the nRT, and nR, of course, constant, so that becomes nR times the delta T. And remember, the delta E was N times Cv delta T. You put that in here, so you get that the enthalpy change will be, the energy change plus an additional Nr delta T. You can put that R into the Cv here, and then you have N times Cv plus R times delta T. Or in other words, the Cv plus R is nothing different than the Cp. So it's N times Cp times delta T. So this comes down to the enthalpy change of the system, okay, irrespective of how you do it. It's going to be number of moles times the constant pressure, heat capacity, times the change in the temperature, okay. Therefore, it means when we're talking about these processes, we have to distinguish between the Q, the heat that is associated with it, the enthalpy, or the energy, okay. Now, what about comparing a constant volume, right, or a constant pressure? Remember that the heat flow, okay, depending on where we do it, at pressure or volume being constant, right, it's always N times C times delta T, but the C can be either a Cv at constant volume or a Cp at constant pressure, okay. And so this means that at constant volume, the energy change is simply the heat flow, but at constant pressure, why do I have two constants here? I'm not sure. At constant pressure, it's equal to the delta H. Okay, now let's focus focus a little bit on this again. What does it mean that at constant volume the delta T, right? So at constant volume the delta E equals the heat. Well, it just means that there is no pressure volume work at constant volume, and so the energy change in the system is directly related to how much heat was liberated or absorbed by it. Okay, this makes total sense. What about at constant pressure? At constant pressure, the heat that is associated with the processes is the change in the enthalpy. And that's why we will be talking about enthalpy, and that's why we sometimes call it heat of something, because if we're talking at constant pressure, the heat in the process is directly the enthalpy change. Okay. So it's a good summary here, and then I recommend that you take a look at this table quite a few times. So first of all, the constant volume heat capacity is 3/2 R for a monatomic ideal gas. Now for a polyatomic, it's larger than that. You can measure the value experimentally, but actually we can do better than that. There's some good theory behind it, so you can actually calculate it too. But anyways, that's not the subject for this class. You can take a statistical thermodynamics course, for example, and the physical chemistry course if you're interested. But for all ideal gases, no matter what the Cv is, right, it's just Cv plus the R to get the constant pressure heat capacity, which takes the pressure volume into account. And so for a monatomic ideal gas, then it would be 5/2 RT, or bigger than that for a polyatomic, not important. And then for all ideal gases, no matter what their structure is, what the value of the actual value of the CV, the energy change is the number of moles times the CV, and then the change in enthalpy is number of moles times the CP, of course, times the delta T. So let's look at an actual problem here. And in this, we will calculate the energy, enthalpy change, the heat, and the work as the system goes from point A to point B on this diagram. Now, what does it mean, point A to point B? We're talking about the y-axis corresponding to pressure and the x-axis corresponding to volume. So point A would be a pressure of 2 atmospheres and then 10 liters, and then the system will expand to 30 liters. At the same time, its pressure will drop to 1 atmosphere. Now, we can do it 2 ways that are depicted here, of course, an infinite number of other ways. First, by doing an expansion from point A to point C, and then we'll decrease the pressure at constant volume from C to D, or we can go this way first to point D, which is 1 atmosphere and 10 liters, no volume change first, just a pressure, and then expansion from 10 to 30. And so we will calculate all these various pathways. And remember, what we should find is that those that are state functions, their change from point A to point B will not depend on the pathway taken, but heat and work, which are not state functions, they can, right? So we'll calculate the Q, the W, the delta E, and the delta H for both of these pathways, which mean, of course, 4 different individual steps. So let's start, and then I prepared these empty screens, but just, what we're talking about here. So let's calculate the first one, right? So the first change is from A to C, in which the delta V, right, is 20 liters, right? So you're going from 10 to 30 liters, okay? And then the pressure is constant. Okay, the pressure is constant, and we are at 2 atmospheres. So how would you calculate this? Well, first of all, remember the ideal gas law. So PV equals nRT. So P delta V equals nR delta T. Okay, and why do we need the delta T? Well, together with the heat capacities, that's what we can use to calculate the heat or the energy changes. So if you rearrange it, then this P delta V here is, and then let's keep it in liter atmospheres. So now the pressure is 2 atmospheres times the delta V is 20 liters, right? And so that would be 40 liter atmospheres. And remember, the 40 liter atmospheres, you can convert it to joules as 101.325 joules for each 1 liter atmosphere. And so that would be, and I need, of course, a calculator here, 4 times 101.325. That would be 4,053 joules, okay? And so the delta T equals 4,053 joules per nR. And we don't know the N, and of course we do know the R, so we'll just leave it like that. And so if I want to calculate, let's calculate the work first, right? That's the simplest. The work is minus P delta V, and we already calculated that, right? And so the work is going to be 2 atmospheres, right, times 20 liters, that's 40 liter atmospheres, and that happens to be because the minus sign of as its expansion, it's 4053 joules. Now, I can round it and all that, but let's not worry about here because we didn't give you the data as, 2.00 or something. Okay, but nevertheless, we have the work. What about the heat, right? The heat in this case, it's constant pressure, right? So it's a constant pressure process, and for a monatomic ideal gas at constant pressure, that's going to be N times Cp times delta T, right? Which is N times 5/2 R delta T. And we have the delta T calculated just before, which is then N times 5/2 R times, and the delta T, the delta T is coming from here, and 4053 joules per NR. The N and the R, they all cancel each other, so it's essentially 5/2 times 4053. I still have that number in the calculator, so I just multiply it with 5/2, and then what I get is 10,001. So let's say 1.01 times 10 to the 4th joules. Okay, so we have the work, and then we have the heat. What about the delta E and the delta H? Now, the delta E, you can obtain it two ways, and let's check both of them actually. So the delta E is, that's always CV kind of thing, right? So it's N times CV times delta T, which is N times 3/2 R times, and then I put in the delta T from here right away. That's 4053 joules per NR. and R cancel each other out, so it's 3/2 4053. And if I do that, then I get 6.08, right? 6.08 times 10 to the 3rd joules. Okay, that's the delta T. Now, delta E. Remember, the delta E has to be equal to Q plus W. Remember? Okay, so let's see if that works. So this is the W here, this is the Q here. And if I add them up and they're still in the calculator, then I happen to get back the same number that this is. So it works. So we didn't make a huge mistake here. What about the delta H? The delta H, as always, is N times Cp times delta T, which is N times 5/2 R times this delta T thingy and R, right? And R, again, cancel each other out, so it's essentially just 5/2. That's 4053, and I take that, and then I get 1.01 times 10 to the 4th joules. What should I get here? Well, remember, this is a constant pressure process, okay? At constant pressure, the delta H equals the Q. And that happens to be the case here. What we calculated for Q also happens to be the delta H. So in the next steps, we may not even do this, but for now, it looks pretty good, right? So we have the delta A, delta H, and then the work and the heat. Now, what about process 2? Okay, so process 2 is when we're going from point C to point B. And essentially, it's a constant volume process, right? Because the volume is kept at 30 liters, right? But the which means that only the pressure changed and the volume did not change. So how would we then calculate the temperature change here, right? And so still remember that the PV, okay, let me write it down here, PV equals nRT, and so the delta PV is still equals N and the R don't change, so NR delta T. Okay, so I can calculate the delta T then as the change in the PV, delta PV divided by nr. And then the change in the PV is, in this case, we went from 2 atmospheres to 1 atmosphere, right? And so that's a minus, that's a negative 1 atmosphere. The volume is 30 liters, right? We're right here. And so that's going to be minus 1 times 30. So it's minus, and then let me just write it down like that, minus 30 liter atmospheres over nr. And now you know how to convert, between liter atmospheres and joules at 101,325. So let me just put that in and then directly write it in there. So that would be 3.0397, so 3.04 minus 3.04 times 10 to the third joules per nr. Remember, we just keep the nr because it will cancel out nevertheless. Okay, so that's wonderful. And so since we have that, then the Q is, since we are constant volume, N times CV times delta T. And for an ideal gas, that's 3/2 R times delta T is minus 3.04 times 10 to the third joule over nr. And as I said, the nr cancels out the n and the r, and so we just have 3/2 times minus 3.04 times 10 to the third. And so if I do that, if I calculate that, that happens to be minus 4.56 times 10 to the third joules. Wonderful. So I have the Q. What about the work? The work is, let's just write it down. P times delta V, negative, right? But the volume is constant. The delta V equals 0, so the work is simply 0. Okay, so the work is nicely 0. And the delta E, okay, for two reasons. You can look at it as Q plus W, okay, or simply N times CV times delta T, okay, because you're at constant volume. So either way is just equals to Q in this case, and so that's the same, minus 4.56 times 10 to the third joules. Okay, what about the delta H? The delta H is always, remember, N times CP times delta T, and in this case, N times 5/2 R times the minus 3.04 times 10 to the third joules over nr, right? That's the delta T. And then essentially it comes down to 5/2 times this value. And if I didn't make a mistake in my calculation, that's minus 7.6 times 10 to the third joules. Okay, so we have the delta H, we have the delta E, and the Q and the W. And remember, in this case, the delta E equals the Q because we are at the constant volume process. So now we have all 4 quantities in the second step. And so for pathway A, from A to B, you can add up 1 and 2. Okay, very nice. So how about the next one in this series for step 3? Let's not overdo it because it's essentially the same. Again, the third one is just like the second one, right? So it's from A to D, which means that the delta V is 0, right? It's a constant volume process. So right away, I write it down here at the end. The W has to be 0. Okay, so that's a no-brainer. And then as before, remember PV equals nRT, and so the delta T equals the delta in the PV over nR. And in this case, the pressure is again 2 to 1 atmosphere, and then the volume, however, now is 10 liters, and so it's going to be smaller. It's going to be minus, the change in the pressure is 1 atmosphere, 10 liters, so it's minus 10.0 liter atmosphere over nR. And then if I multiply it 101.325, then it happens to be 1.013 times 10 to the third joules per nr. So we have the delta T the same way. The work is 0, and let's calculate then the Q. The Q is constant volume, right? So N times CV times delta T, and that's N times 3/2 R. This is getting boring, right? So the delta T is minus 1.01 times 10 to the third joules per nr. As usual, nr cancels out the nr, and so we're left with this minus 1.01375 to the third times 3/2, and that is minus 1.52 times 10 to the third joules. Okay, so we have the Q. The delta E as before equal to the Q, and this is still minus 1.52 times 10 to the third joules. What about the delta H? The delta H is N times Cp times delta T, always, right? And that happens to be N times 5/2 R times minus 1.01 times 10 to the third joules over nr, bam bam, and that is then minus 2.53 times 10 to the third joules. So we have the delta H, we have the Q, we have the delta E, and of course the work is 0 because it's constant volume. All right, so we have the third one as well. Very, very nice. What about then the fourth process when we're going from D to B? Okay, again, this happens to be, so number 4, right? It happens to be a constant pressure process, right? The pressure is 1 atmosphere, right? The volume is from 10 to 30, that is 20 liters. And remember, PV equals nRT again. Let me just give you the result. So the delta T equals P delta V divided by nR. And then the pressure is 1 atmosphere. The volume changes 20, right? So it's going to be a positive 20 liter atmosphere over nR. And then converting it to SI, it's going to be 2.03 times 10 to the third joules per nR. Okay. Again, I'm doing just, the same thing as before. And let's calculate, let's say the Q first. So the Q equals N. It's a constant pressure, so it's Cp times delta T, and so it's N times 5/2 R. The delta T is 2.03 times 10 to the third joule per nR. nR cancel out, so it's 5/2 that value. So 5/2 times this is going to be 5.07 times 10 to the third joules. Okay, so it's 7 or 08, it's 07. Okay, times 10 to the third joules. Now, what about the work? The work is minus P times delta V. The pressure is 1 atmosphere, delta V is 20 liters, so it's minus 20 liter atmospheres. Which of course happens to be, we already calculated it here, it's minus 2.03 times 10 to the third joules. Cool. So we have the work, which is negative, we have the Q, which is positive. The delta E can be calculated two ways, and since on step 1 I calculated as N times Cp CV times delta T, sorry. Now I can just calculate as Q plus W, right? Because it's always the delta E. And if I add up these two values that I just calculated, okay, the Q and the W, then what I get is 3.04 times 10 to the third joules. That's a delta E, and I'm happy. And the delta H, okay, is usual n times Cp times delta T. But I also know that this is a constant pressure problem, so let's not even worry about that. I just know it has to be the Q, right? Because that's why I call it heat and constant pressure, right? So it is 5.07 times 10 to the third joules. Okay, awesome. Now, I calculated again all four quantities here. And so now I have all four quantities for all four processes. And now I can add up 1 plus 2, going from A to C to B. And then I add up 3 and 4, going from A to D to B. Okay, and then again, essentially I went from A to B, and all those quantities that are state functions should be the same. So here are all the numbers. If I calculated them right, I hope there may be some rounding differences, but nevertheless, if you add it all up, then let's just check, let's say, the delta E. So 1 plus 2, okay, equals 6.08 times 10 to the third minus 4.56 times 10 to the third, which is 1.5 times 10 to the third joules. And then the second one, 3.05 times 10 to the third minus 1.52 times 10 to the third. And that is messed up in my calculator. Oh, because I forgot the third. 3.05 times 10 to the third is saying 1.5 times 10 to the third joules. Okay, so it totally makes sense. If you go this way or if you go this way, then the associated delta E is going to be the same because it's a state function. But let's look at something slightly different, right? What about the work, right? That's an easy one because the work here is 0 and the work here is 0. And so on the first path, this is the net work. Okay, the system was doing 4.05 times 10 to the third joules. And in this case, it was doing minus 2.03 times 10 to the third joules. And so the work 1 is not equal to the work 4. Right, or the work on path 1 is not equal to the work on path 2 because the work is not a state function. It does depend on the pathway. And in fact, it's kind of easy to see how, right? The area here that is shaded in purple, and now it's red, is, the volume change times the pressure it's going at. And here, it's at lower pressure, the volume change is the same, and so you can see that indeed the work that is in the process 1 is twice, right? This work is twice the other work. Okay. And so again, the take-home message is first we can calculate all this, and this is important, right? And then practice this. This is not an easy problem, right? Go over each step and calculate each step, understand how what we're doing and what are the underlying assumptions. Again, talking about a monatomic ideal gas, but also that the delta E, no matter how we do it, we get the same value. It's pathway independent. We would get the same thing for the delta H. If you add up these two values and if you add up these two values, you should get the same thing. Except if not, then there's some issue here. But I hope you do get the same. But then the work and the heat are not the same. Okay, so we can go back. Or the calculations are here. The delta H. There's something that looks a little bit off, but nevertheless, when you add it all up, then the delta H is a state function, got to be the same. Okay, so this leads us to something a little bit more practical also, because it's in the lab that we are doing. Calorimetry is a way to determine the heat of a chemical reaction. Essentially, it's the science of measuring heat, calorimetry, but it's usually used more specifically when we measure the change in temperature and then calculate the heat associated with a certain process through that. The temperature change, okay, and then the heat that is absorbed or given off is related through, the heat capacity that we already discussed. And so this heat capacity, as we've seen, is proportional to the number of moles, but of course it's any other measure of the amount of the substance, so it's proportional to how much substance you have. You can express it per moles of the substance, right? The molar heat capacity, as you've seen, we called it CP or CV, and the unit was joule over mole Kelvin. But you can also, and then this is how it was traditionally done, you can refer it to mass of the substance, and it would be, the SI unit would be Kelvin over kilogram, but typically would not working with kilograms, so it's typically we express it as joule over Kelvin times gram, or joule over Celsius grams. Now, this is a tricky one here, right? Because in chapter 5 was very adamant that don't ever use Celsius, use Kelvin, right? If you let's say do a temperature change from -10 to +10 Celsius, then if you look at the the ratio of temperatures, and you get a negative value, which of course is insane, right? But here, what we're talking about is always delta T, right? And the delta T, that is a change in temperature, is the same measured in Kelvin or in Celsius, because the two scales are simply shifted with respect to each other, right? Kelvin starts out with absolute temperature, absolute zero, as its 0 point, and Celsius has a 0 point as the melting point of ice, but nevertheless, the graduation is the same on both. So when we're measuring delta T, it is okay to use Celsius. If you're measuring absolute temperatures, then it's not. And these are some heat capacities. Again, you don't have to memorize this, but just look at this value that is fairly high, right? So liquid water has a very high specific heat capacity, which means that water can store a lot of heat in it. So that's why, for example, if you live in the Bay Area, then it's never really very hot in the summer, because the cold ocean body cools it down, and it's never very cold in the winter either. Well, too cold for me, but it's because again, the large amount of water there can store a lot of energy or give it back. Now, typically other substances, let's say mercury here, has much more than an order of magnitude lower heat capacity. So water has very high heat capacity indeed. And remember, the heat capacity is associated with ways that the substance can absorb energy, right, and raise its temperature. Now, how it can do that, a monatomic gas, is simply with translations. Let's say a diatomic gas can also do either vibrations or more rotations. Even larger molecule has various vibrational modes in there, so it can store more energy. But then it also depends on the phase, right? If you're talking about not gases, but liquid water or solid water, then those are very different, right? Because then the interaction between these molecules comes into play as well, and liquid water actually has the highest heat capacity here. Now, how can we use this calorimetric thing? And then let's look at, for example, this simple setup. Now, we should be doing this in a so-called Dewar flask, and in a Dewar flask, it's a double-walled. It's like a hydro flask. You probably know what a hydro flask is, right? And then here you have vacuum, which means that there's very little heat loss to the surroundings. And so if you fill it up with something cold and then you go golfing, then even by the 18th hole, your drink is still cold because there's very little heat exchange with the surroundings. Now, hydro flasks are insanely expensive because, they're hip. And so we're not using hydro flasks in the lab or in general thermoses, right? Thermoses, that's also actually... It became like a common name, but it's also a brand name. And we use just simply styrofoam cups. And if you take two nested styrofoam cups, then the heat loss to the surroundings is pretty small. And then what you do is you also have a cover. So that's very important, actually, because a lot of heat, especially high temperatures, is lost through there. And then you put in a stir and the thermometer. And then this would be a so-called constant pressure calorimeter, right? Because the pressure in there throughout the reaction is the same as the outside pressure. Then you can measure the temperature change and determine changes in the enthalpy, because the change in the enthalpy, right, at constant pressure equals the heat. So how would we solve such a calorimetric problem? So in this coffee cup calorimeter, we put in 50 milliliters of a 1 molar HCl and 50 milliliters of a 1 molar NaOH, and we mix them at room temperature 25 Celsius. Let's say 25.0 or whatever, okay, because the next one is given as 31.9 Celsius after the reactant mix and the reacted temperature increase. Now, what's the reaction? Well, it's the neutralization of HCl with NaOH going to sodium chloride plus water, right? And then if you want to write the net ionic equation, it will be just proton plus OH minus going to water. So what would be the reaction heat for this? How would we get this? Well, first of all, we have to look at the temperature change. So the delta T is 31.9 Celsius minus 25.0 Celsius, and that is 6.9 Celsius, okay? And the mass of the solution, how do we know that? Well, these are both fairly, well, not very dilute, but at least most of it is definitely water, right? And so the mass is going to be the volume of the solution, which is 100.0 milliliters, times the density of water, which is 1.0 grams per milliliter. So we have 100 grams. Okay, and again, I'm not trying to indicate the number of significs, but we have 100 grams of a solution, and the temperature changes is 6.9 Celsius. But how do we know the specific heat, right? Because the Q here is N times C times delta T. And so the heat capacity is needed here, but it's mostly water, right? It's 100 grams of water, and if you calculate, that would be a 0.05 moles of HCl. So it's mostly water. Therefore, we can use the heat capacity of water in this case. So it's 100 grams times the heat capacity of water, which is 4.18 joule per gram Celsius, and what was it, times 6.9 Celsius was the temperature change. And if I multiply it together, let me put this into the calculator, 100 times 6.9, and then I get 2.9 times 10 to the third joules. Okay, remember, don't round it here yet because we still do calculations, so keep the original number in your calculator. Now I want to express the delta H R in terms of joules per mole, right? So per mole of reactants. So how many moles of the reactants I have? So the number of moles of the HCl, and I use the same amount of the two, which is the number of moles of the NaOH, which is the number of moles of the reaction, okay? And that happens to be 1.0 moles molar times 50 milliliters, so it's 0.050 moles, all right, or 5.0 times 10 to the negative 2 moles. And so then the delta H R is 2.9 times 10 to the third joules divided by 0.050 moles. Now, let's pause here for a moment. Okay, what about the sign? Okay, remember the Q is, how do you look at it? Well, the Q is the energy from the system's perspective. But the temperature went up, which means that the surroundings were heated up. From the system's perspective, that is negative, right? And so the delta H, this is an exothermic reaction. It heated up, heat left the chemicals. The products are in a lower energy state than, or enthalpy state, than the reactants, and therefore it's a negative sign, right? Always remember that when you're calculating thermochemistry, it's not just the quantity, but also the sign. Okay, I've preached that enough, and so if I divide it by 0.05, I get minus 58 kJ per mole. Very good. Okay, so with this, we could determine what is the reaction heat or the reaction enthalpy for the neutralization between HCl and sodium hydroxide. So this is how you would do a typical calorimetry problem. But what about, let's say in this case, a precipitation reaction. Okay, so let's do a precipitation reaction here. What we do is we mix 1 liter of 1 molar barium nitrate with also 1 liter of 1 molar sodium sulfate. Remember, sodium sulfate and barium nitrate react, form a precipitate, which is not sodium nitrate, but barium sulfate. Okay, so this barium sulfate is formed. And then during that, the temperature increased from 25.0 to 28.1 Celsius. So the delta T is 3.1 Celsius. And then the calorimeter absorbs only a negligible amount of heat. This is a very well insulated system. It looks ugly though. It looks like it's like a bath or something. Anyway, so what is the specific heat capacity of solution? Well, it's still mostly water, right? And so you use this heat capacity of water. And again, since it's still mostly water, the density is the same. Now, of course, this is probably a good approximation, but not perfect because barium is actually very heavy. It's a very high density salts. Anyway, so what would be the enthalpy change per mole of barium sulfate? So how would we do this calculation? Very simply, if you still remember, the mass of the solution is going to be 2.00 liters times, well, let's convert it to milliliters first. So it's 1,000 milliliters per 1 liter, right? And then the density is 1.00 grams per milliliter. So that happens to be 2.0 or 2.0, whatever, times 10 to the third grams. Okay, so the mass of the solution is essentially 2 kilograms or 2,000 grams. The delta T, I already said, it went from 25 to 28.1 degrees, so it's 3.1 Celsius was the temperature change. And then so the Q that evolved, okay, so let's put the negative sign in, right? From the system's perspective already, it's going to be M times the C times the delta T. And so 2.0 times 10 to the third grams times 4.18 joule per gram Celsius times 3.1 Celsius is the temperature change. And if I punch it into the calculator, 2000 times 4.18 times 3.1, you get minus 2.59. So let's say 2.6 times 10 to the fourth joules. Okay. And so the delta H, and we're forming 1 mole, right? So the delta H is minus 26 kJ per mole. Nice. Okay, again, same business. We pretended it's all water, which is a very good approximation, which gave us the density, that gave us the mass, and then we use the specific heat capacity of water to do this calculation. So this is how you can do calorimetry calculations very simply. Now, let's switch gears here just a little bit. And let's go into pressure volume work again, just a bit. How could we do that? Well, first of all, if we have reactions that are going on in solution, right? Typically aqueous solutions for us, then there's no appreciable volume change, right? There are tiny little volume changes, but not much, and so therefore the work that we have is zero, and so the delta H is roughly equal to delta E. How about when there's a mole change in the gases, right? If, let's say in this case, what could this stand for? Let's say this is SO2 plus O2 going to 2 SO3s, right? Yellow typically means sulfur, if you forgot. We start out with 3 moles or 3 units of a gas on the left hand side and then turn into 2 on the right hand side, and so there is an appreciable delta V, which is not 0 but much less than 0, right? So there's a negative volume change, and therefore there's some pressure volume work involved according to the negative P delta V. And remember, at the constant pressure, the delta H is what's equal to the Q, and the delta E, as usual, is Q plus W, and so the enthalpy change is related to energy change through that extra work. And then of course the important thing is that the delta E and the delta H are different in this case, okay, because there's a change in the volume. So how could we actually do this in a specific calculation, right? And so in this case, it was so far good. We have 2 moles of SO2 and then reacted with 1 mole of O2 and then from 2 moles of sulfur trioxide. The temperature is 25 degrees, the pressure is 1 atmosphere, and then we noticed that 198 kJ of energy is released is the heat. What we did the delta H and the delta E in this process is, remember, the two are interrelated to the so 198 kJ. Let's try to remember that. There is I didn't leave much room for this, so let's try to do it here. And so that is the Q, and remember we're talking about a constant pressure process, and so in the constant pressure process the delta H is equal to the Q, and it's released that heat, so it's minus 198 kJ. Okay. What about the delta E? Remember from the previous slide that the delta E is equal to delta H plus the work, and then the work is, so it's delta H minus pressure times delta V. So the work is simply the pressure volume work. So how could we get the delta V? Again, what we can do is use the so it's a constant temperature actually. So the temperature, right, is constant. Okay, the pressure is constant. So then the delta V is related to what in the PV equals nRT? Well, let's write it here. PV equals nRT. Well, so this guy is constant. This is the universal gas constant, and the pressure is constant. And so what is it? Well, the number of moles, indeed. And so the delta V equals delta N times RT over P. And the delta N in this case is going from 3 moles down to 2 moles. So the delta N is minus 1 mole. Okay. And so now we have everything to get this calculated. And so the work here is minus P delta V, and I don't have a lot of room. Sorry about that. And that would be the pressure. right? Now we can do it in liter atmosphere, right? But of course that would be an ugly one in the end because we want joules. And so what we have is the work, right, equals minus P delta V, which is minus P, and then there it is, delta N times RT over P. And so luckily that atmosphere cancels out and we have minus delta N RT, right? And the delta N is minus 1 mole. So essentially we end up being RT times 1. And so it's again minus, okay, minus 1 mole times 8.314 joule per mole Kelvin, this is joule, times the temperature, and the temperature is 25 Celsius, so it's 298.15 Kelvin. And then if you put that all together, then remember minus end up being a plus. Okay, so let's come back to that in a moment, but 8.314 times 298.15, well, it's well on quantity, right? So it's 2.48 times 10 to the third joules. So I can just write it down as kjoules. And so the work is positive. How come it's positive? Haha, because the delta V is negative and it's minus delta V. So it's the surroundings doing work on the system and not the other way around, and therefore the pressure volume work is positive. And so now we know the work, and the delta E would be, the delta H plus this 2.5, so it ends up being 1 minus, and so the delta E is minus 196 kjoules in this case. Okay, so well, the slide looks pretty ugly and written over, but hopefully you could follow the derivation. Essentially just coming up with what was the pressure volume work and then putting it in to the delta H to get the delta E. Now, how about those processes where it's not the pressure that is constant, but the volume that is constant? We call that bomb calorimetry, that constant volume. That is, no work is done, okay? You take the reactants and then place them inside a rigid container. Typically, they're made of stainless steel because oftentimes, as its name suggests, they blow up, right? And then you ignite it. This is how you do that, right? You can spark it and then ignition starts. And then the work is 0 here, right? And so in this case, the energy change is associated with the heat. It's a constant volume process. And this is, for example, a typical bomb calorimeter. We do bomb calorimetry in experimental physical chemistry. One of our high-level courses, I believe we call it 167, Chem 167. So if you're interested in physical chemistry, I sometimes teach that course. It's totally awesome. So then you can do some bomb calorimetry. So let's use an example here. That would be a bomb calorimetry of octane combustion. Octane combustion, of course, is fun because octane is, of course, gasoline, one of the principal components of gasoline. Well, isooctane, technically, but never mind. So we take 0.5269 grams of octane, place it in bomb calorimeter, and then the heat capacity of the bomb calorimeter, which includes everything. So that's why it's a bit complicated here. The container is insulated, right? But it's surrounded by water, which will suck up the heat. In the center, you have the bomb and then the reactants in the sample cup. And then the way to do this is that you have an ignition wires here that starts a reaction, but typically you also put in another set of wires, essentially as a resistors, and through electrical heat you can put a very known amount of energy into it and then measure the temperature change, and that way you can calibrate your calorimeter. This is very important. But for now, we just have the heat capacity of the calorimeter itself. So what we do is take the octane, ignite it with excess O2 and then measure the temperature change, and the temperature increased by 2. So the delta T is 2.25 Celsius. Before I forget. And so we have the heat capacity with calorimeter, and that was 11.3 kJ per Celsius. And so the heat, which of course in this case is the delta E, is, well, I guess that would be the minus of it, but anyway, I'm not defining which way. Looking at it is 2.25 Celsius times 11.3 kilojoules per Celsius, and that gives me 25.4 kilojoules. Okay, and so this means that, okay, and then, you know, let's put in minus because it just looks ugly otherwise. So this is the amount of energy that was released in the combustion of this much octane. But how much octane do we have? 5269. So the mass is 5269 grams of octane, right? But I want to calculate in moles, right? So let's convert it to moles of octane, and then 1 mole of octane is 114.2 grams of octane, right? And so if I put that in my calculator, 0.5269 divided by 114.2, that would give me a very small number. It's 4 point, I think my calculator is in the wrong mode. Oh yeah, let's put it to float. Okay, now that my calculator is floating, it's 4.61 4 times 10 to the negative third moles. Okay, and so if I want to get the delta E of the combustion, right? And I put a C here for combustion, cool, is minus 25.4 kjoules divided by 4.614 times 10 to the negative 3 moles. And if I do that, and I hope I got it right, so where did I have that number? So 2.25 times 7.3, right, divided by that. And I get 55 kjoules, 55,000 kjoules per mole. So let's write this 5.5 times 10 to the third kjoules per mole. So the combustion heat, okay, is minus 5.5 times 10 to the third kjoules per mole. But here, since it's a constant volume, the heat equals the delta E and not the delta H, right? Because no work was done in this process. All right, nice. And then I think the pretty much the last part of the chapter, but hands down my favorite one is Hess's law. Now Hess's law is just a fancy way of stating that energy, or in this case enthalpy, is conserved. Enthalpy is a state function, and so if you go from an initial to a final state, it's independent of the pathways. And so let's say we have a reaction between nitrogen and oxygen going to nitrogen dioxide, and the reaction heat is 68 kjoules per mole. We can carry out this reaction in one, going from N2 directly to NO2, or we can do it in 2 steps. We can do it in a different pathway. First, oxidizing the nitrogen to nitrogen monoxide, and taking this nitrogen monoxide and oxidizing it further to NO2. And we can measure the individual heats of the reaction. The first one will be 180 kjoules per mole, and the second one is minus 112 kjoules per mole. And since the initial and the final states are the same, That is, if you add up the two reactions, then it simplifies down to nitrogen reacting with two O2s going to nitrogen dioxide. If you add these two up, you have to get the same thing as if you did the reaction in one step. And if you add up these two numbers, you recover that same 68 kJ per mole. And so this is very handy, because what this means is that if you add up, let's say if you were to determine, for example, the reaction heat for N2 and O2 going to nitrogen monoxide, then you can measure this reaction here, you can measure this reaction here, and then the difference of the two would give you the missing heat of formation. Okay, let's visualize it so that it becomes more evident. So if you start out with these reactants, whether you choose a pathway that first converts into nitrogen monoxide, which by the way looks to be massively endothermic, and then in an exothermic process you further oxidize it to NO2, or you just do it in one step, going from nitrogen and oxygen to nitrogen dioxide, the sum of these two arrows will be the same. So it doesn't matter which way you do it. If the reactions, these two reactions, add up to that reaction, then the reaction enthalpies will have to add up to the same value. And in fact, this is one of my research areas. That's why I'm so enthusiastic here. And then a few years ago, when maybe more than a few, we published, this is probably my favorite paper ever, a paper on the protonation of water, right? And what we did was, with our technique, essentially we can ionize a substance in gas phase and then fragment it, and we can measure it very, very accurately. So in this case, for example, we took a water dimer, which under some very peculiar experimental conditions, two water molecules can stick together in a gas phase, forming a dimer. And if you ionize and fragment it, it can go to the H3O plus and then the OH. And you heard about H3O plus quite extensively, right, in chapter 7 and 8 and all that. Right, so we can measure this quantity, okay, and then similarly, if we just take water and then the extra water just so that it adds up to the same number of species, we can fragment it to the OH plus and then a hydrogen atom, right, and then I did one extra water so that it all adds up, and then somebody else, it was actually down, I think at USC by the Reisler group, they measured the dimerization energy of water, so the difference between these two here, and then this is well known, this is well known, and so you can put together this thermochemical cycle, and with all these quantities, the one missing link here is what you call the proton affinity of water. What is that? Well, it's between a water molecule, right, and an H plus into this hydronium ion. So this is really one of the most fundamental processes, right? Let me just write it down for you because it's so cool, right? It is water picking up a proton and forming the hydronium ion, right, that we always talk about. And so with this thermochemical cycle, we could actually measure it. And so these are all our experimental values. Then this was the literature value for ionization-enriched hydrogen and OH radical. Then this is coming from the Reisler group, and then these two quantities we measure, and that add up to the proton affinity of water. And the cool thing about this was that this is more than an order of magnitude more accurate than anything that was available up to that point, and also it represented a significant correction to what was in the literature, right? So this is not just, a textbook topic. This is actually real cutting-edge research that is going on currently. All right. So at a somewhat lower level, how can we use this Hess's law to carry out calculations? So first of all, we need to know how to manipulate this delta H. So quite evidently, if we reverse a reaction, so write down an equation for reaction and then flip it, then the sign is reversed, right? Which is, of course, making sense, right? Because if a reaction is exothermic in one direction and it's going backwards, it has to pick up the same amount of heat. Also, if you multiply a reaction, right, then the delta H will multiply, right? So the delta H is proportional to the quantities, okay? So if you multiply all the stoichiometry coefficient by a factor, then the delta H will multiply the same factor. And so now we can put all this together and use a bunch of individual steps that somehow add up to this reaction. And if we know the individual delta H values, somehow the book likes to use kJ. Please don't. It's kJ per mole of the reaction as it's written, okay? Then we can come up with the delta H for this. So these are the values. And again, just so that I can sleep well, let me add this per mole, okay? And then let's add them up in a way that we get the heat of formation of this. So how can we add up these reactions so we get the final reaction? Well, let me show you how this goes. So first of all, we need 2 borons on the left-hand side. So let's choose a reaction. This is a reaction A, B, C, and D. Let's choose an equation that has 2 borons on the side. Or if not 2 borons, then let's multiply it up. But luckily, reaction A has just that. So let me write it down. 2 borons, and I will leave all the states out, except for water. You see why? Right, this is the first reaction, and it's minus 112.73 kJ per mole. Then I also know that I need this guy, diborane, on the right-hand side. So let's choose a reaction that has the diborane on the right-hand side. Well, I don't have one, but if I flip this one, then it's going to have it. So if I flip the second reaction, reaction B, then I have oxygen, right? And on the left-hand side, I have boron 3 oxide and 3 gaseous waters, and I write out the gas for water because there's more than one state here. Okay, so what will be the delta H? Well, I flipped it, so the minus 2035 would change sign, so it's sign to plus. Okay, so it's pretty good for 2 reasons, and then let's change color here. That this guy cancels out that guy when I add them together, but I have the 2 B's and I have the diborane on the right. Of course, the arrow is there. So what else do I need? Well, I need hydrogen. Okay, I need 3 hydrogens on the left. So let's take this reaction here, multiply it by 3, and then I can write this. 3 hydrogens plus 3 halves O2, okay, we'll go to, have I missed something? No, go to 3 liquid waters. And the reason I wrote out the liquid water is just to distinguish it between, gaseous water here. And so this was reaction C, but I multiplied by 3, so it's going to be 3 times minus 286. Okay, again, kJ per mole. Now, let's see what we have. Well, we have 3 hydrogens on the right, which is pretty good. Let's see the cancellations again. So I have this, which I'm happy with. I have 3 halves O2 here, and 3 halves O2 here. And then, of course, that would mean we have 3 O2s, the sum of those 2, and we have 3 O2s here. So this 3 O2 cancels out these 2. And so what I'm left with is simply the reaction I want. So I have this guy, and that guy. And unfortunately, I still have gaseous water on the left and liquid water on the right. But I can just add up another reaction here, and let's switch back to my original color and cancel it out. So what I want is liquid water on the left, gaseous water on the right, and 3 of them to cancel out. And then this is nothing more than 3 times the last reaction, 3 times reaction D. this guy here. And so 3 times 44 will account for the heat of this. Well, you can call it reaction, but this is just, the vaporization heat of water. And so now, again, switching back and forth between colors, you can see that liquid water cancels liquid water, gaseous water, and then I'm just left with the 3 quantities I want. So 2 borons plus 3 hydrogens going to 1 diborane molecule, and the heat that is associated with, I just sum up all these. And if I do that, minus 1273 plus 2035 minus 3 times 286 times 44, and what I get is 36 kilojoules per mole. And I hope I haven't made some horrible mistake, but based on these 4 reactions and then mixing them up in a way so that you recover this equation that you wanted, you can determine its reaction heat, and it happens to be a positive 36 kilojoules per mole. Very nice. Another way of utilizing this Hass's law is to, let's take the problem. Okay, let's say I'm interested in a reaction heat for a particular reaction. What should I do? Well, I can either measure it or I can look at it on a table. But imagine how long the table would be that contains all these reaction heats. It would be enormous. And so can we instead tabulate only a much smaller number of reaction heats that correspond to some agreed upon way of getting to a compound, and then using Hass's law to put them together into the reaction I want? And that's exactly what we want to do. We will define these enthalpies of formation, and let's go back to red. These enthalpies of formation will be defined as the enthalpy change upon the formation of a mole of a compound from its elements. Okay, and from its elements everything is in their standard state. Now, what is a standard state? But let's say what we're talking about. So instead of tabulating every single reaction heat there is, what we'll do is for each compound, we'll just write down what is the reaction enthalpy from its element. And then since the elements on the left and the elements on the right in any chemical reaction has to add up, right? That's what balanced means. Then we can use up these values in Hass's law to get the reaction heat for any such compound. And I'll show you how that works in a moment. But first, let's talk about this reference state. So what are the standard states? So if you have a gas, then its pressure is going to be 1 bar. The book says 1 atmosphere, but that's BS. Okay. For a solute, it's got to have a concentration of 1 molar. Okay. And then under a pressure of 1 bar, if it is a gas over it. And then for any pure substance, the pure liquid or the solid. And if you have an element, then it's the most stable form under ambient conditions, that is 1 bar, and then the temperature of interest, for example, we can talk about room temperature 298.15 Kelvin. And so it's also important that the standard state is different depending on which element we're talking about. It can be a solid, it can be a liquid, or it can be a gas. So for carbon, for example, the standard state is graphite. That's the most stable form under these conditions. For bromine, it's liquid bromine. But for oxygen, it's, for example, gaseous oxygen. Or you can look at the halogen element, and then it's all over the place. For chlorine, it's chlorine gas. For bromine, it's bromine liquid. And for iodine, it's actually solid iodine. Okay, so just know what we're talking about. And so what we do is these enthalpies of formation will be given per mole of the product or mole of the reaction that has 1 mole of that particular compound as a product on the right, and the left-hand side will just have the elements so that it adds up and it's balanced. And then the reaction heat for such a hypothetical reaction, and it's important to say that in many cases you cannot actually do this, right? For anything more complicated than, just a few atoms, there is no such reaction that you mix up. Let's say, extreme example, take DNA, right? Can you carry out a reaction that has a bunch of carbon, hydrogen, oxygen, nitrogen? Is there anything in? The phosphorus. Anyway, something. I'm not a biochemist really. On the left, and it just ends up being DNA on the right. And so these are hypothetical reactions. But if you were to carry it out, then that would be associated reaction heat, and we call these enthalpies of formation. Or, to be honest, we never call it that. We call it heat of formation. Okay. So, as you say, as I said already, this is kind of my research, right? So, this is another paper that was quite a while ago. In fact, it was in the year when I came to Pacific, so it was still with colleagues at UNC Chapel Hill. And so in this case, what we did was we measured both chloroform and then bromoform, and then the various mixed substances, and then came up with heats of formation value for these various mixed haloform compounds. And so this is actually what I do in my research. We determine heats of formation data for various compounds to more accurate, like smaller error bars and anything else. Okay, so let's see how we can use this. If you tabulate these heat of formation values, then you can use to calculate reaction heat. So let's look at, for example, how we can use this for the combustion of methane. So methane reacts with 2 oxygens, goes to CO2 and 2 waters. And since enthalpy is a state function, we can use Hess's law. Okay, choose any pathway. And the pathway we will choose is taking all the reactants and then turn them into the elements, okay? And then from the elements, we'll reconstitute the products, okay? And so if you use these steps, then the individual steps will all refer to the formation enthalpies or heats of formation. So let's visualize this. So the one step is going to be between methane, CH4, and then carbon, graphite, and then 2 hydrogen molecules, okay, the elements. And then this is essentially the opposite, the negative of the heat of formation of methane, right? Because heat of formation will be from here to there, and so this is the negative of the heat of formation. Now, this guy is easy, right? Because it's element to element, so that's just a big 0. And then this one will be the heat of formation of CO2, right? Negative 394 kJ per mole would be the heat of formation of CO2. That will be from 1 carbon and then 1 of the oxygen molecules. And then this here is we're taking 2 hydrogens, 1 oxygen molecules, and form 2 waters. And so this would be twice the heat of formation of water. And so we have 3 heats of formation that we use. And if we add up, then what we have is a heat of formation of a product, heat of formation of this product, multiplied by 2 because we have of them, and then minus the heat of formation of methane. So let's see how this works in general. Okay, how can we use then these heat of formations to calculate the reaction heat of pretty much anything? And so what you do is sum up the heats of formation values for the products, subtract the heat of formation values for the reactants, and if you subtract the two from each other, you get the reaction heat of any reaction. And so now what you have to do is just tabulate all these heat of formations, and then use the heat of formation products and then the reactants. And such a table could look like this. In fact, it's actually very much active research. There's a lot of work put into quantifying these enthalpies of formation. And if you're really interested in it, go to the Oregon National Lab has a website dedicated to an active thermochemical table that lists these standard enthalpies of formation to a very large accuracy. And so you can take these numbers and then calculate the reaction heat for pretty much anything. So a summary of these calculations. Remember that if you reverse a reaction, the magnitude remains the same, but the sign changes, right? If you take a balanced equation and then you multiply it, then the value will be multiplied by the same factor. And if you take these heat of formation values for the products and the reactants, then the difference of the two will give you the reaction heat for any compound. Remember, elements in their standard states are not included in the calculation. Because the heat of formation for element in standard state is 0. But again, this is in standard state. So for example, for gaseous iodine, it is not 0 because the standard state is solid iodine. Okay, so if you compare these reactions, H2 plus Cl2 versus H2 plus I2, okay, everything is gaseous here, then in one case you won't have to worry about the reactants at all because they're both element in a standard state, but in this case you have to take this into account. Okay, just a fair warning. Now, again, as I said, this is all very much active research, and for example, this is one thing we do, and sometimes for, of course, or typically for much more exotic systems than what you've seen in the table. So in this work, which we carried out actually recently, was kind of cool. It's methyl peroxy radical. So this species here is actually very, very reactive. It only lives like milliseconds or so, and it's not like complete compound. There's an atom missing, and so with this. With these worked when we measured the energy that is needed to form two well-known O2 and methylcation, we could get a very accurate heat of formation for this species, and that is what we publish. And then these a lot of this work is then put together and then end up in these thermochemical tables that you can use for determining reaction heat for anything else. All right, so let's do example calculation that is coming from the textbook. For example, if we are reacting ammonia with O2 and form nitrogen dioxide and water, how could we get the reaction heat using the enthalpies of formation? So what we need to do is use the enthalpy of formation for ammonia, the opposite direction, right? So taking it apart into its constituent elements. Then O2 just goes to O2, so this would be 0, right? And then when you put nitrogen together with O2, you can form an O2, and then some of the oxygen will be used with the hydrogen to go into water. And so, again, what was the reaction? 4 ammonia plus 7 O2, I haven't forgotten, goes to 4 NO2s plus 6 waters. So what is the reaction enthalpy for this particular reaction? And so what we have to do is this delta H equals the formation enthalpy for the products minus the reactant. So the product is NO2, which is 34, but you multiply by 4, you add up the heat of formation for water. Sorry, I cannot say enthalpy in this. It's built in. 6 times minus 286, right? And then you subtract 4 times the heat of formation of ammonia, which is minus 46. Everything is in kJoules. Right, and if you add it up, and then what about oxygen? You know, oxygen is an element in standard state, so we don't do any of that. So minus 96 kJoules per mole. Okay, did I do it correctly? I hope I did. Okay, so we We put all that together, and then they add up to the heat of the reaction for this particular one by using the heat of formation values from the table. All right, so now we really went through Hess's law, again, a particular aspect of Hess's law would be with these heat of formation values that you can use to get reaction heat, and then also please practice those Hess's law problems where you have a set of reactions and then you mix them into the target equation to get its reaction heat that we did first with the diborane. So this was really the interesting part of chapter 9, and then I just have a few more slides left about energy sources, and I will just go quickly through this. First of all, because it changes really every day. Now there's a lot of talk about global warming, and so now energy sources that were considered by previous administrations, the best and cleanest, are now some suddenly seem like the worst. And it depends very much on countries too. So let me just give you a quick overview. We'll talk a little bit about these energy sources at petroleum, then it's usually associated with natural gas, then coal, which gets a lot of bad rap recently, then nuclear energy, hydropower, and maybe some others too. And so you can see that over the years, how much of these various energy sources were used changed enormously. Well, in the mid 1800s, it was mostly wood, and then coal became the major player. Simply because the energy density is much higher than of wood. And then, of course, there are ample deposits in many places. Then in the mid 20th century, petroleum and natural gas together started to take off, partly because it's a lot more convenient, right? Natural gas is a gas on pipelines. It can be transported to large distances. If it's liquefied, it can be taken on giant ships, or petroleum, of course, is the most convenient energy source of all because it's liquid, high energy density, and all. And by the mid, by the late 20th century, petroleum and natural gas together were by far the biggest energy source. But then the first, explosion of the oil prices caused actually a decrease in the quantity and the amount of coal came up, which is now, biting us in the rear end because of global warming, coal is exactly what you want to phase out. And interestingly, the reason why coal came back in this country was that one of the previous Democratic administrations, Carter, were faced with the choice: should we go towards nuclear? Should we go towards coal? And that back then there was a technology called clean coal, which reduced the other pollutant in the process. But of course, CO2 is always there when you're burning coal. And then this administration decided to go towards the coal industry and then invest heavily in that. And therefore, it actually increased over the year. And now pretty much the same people are trying to phase this out. So it's, the irony is quite interesting. Now, hydro and nuclear are also coming up, but it's very country-dependent. So remember, France and Germany, for example, they are next to each other and have totally opposing views about the role of nuclear power. So let's start first with a little bit with petroleum and natural gas. It was formed, about 500 million years ago from the remains of marine organisms. Petroleum is a thick and dark liquid, and it's mostly of hydrocarbon chains between 5 and 25 carbons. Shorter than that, it's in a gas. Longer than that, it's just too thick. And then depending on the length, there are different fractions that we may be interested in. Gasoline, the lightest fraction, is between 5 and 10, most notably 8, and 7 as well. If it gets longer than that, you have kerosene or jet fuel. Even longer than that and thicker than that will be diesel fuel or heating oil, even thicker lubricating oil. And then the cool thing about petroleum is you can use every little bit of it. That's why it's like a magical substance. And then the really longest ones, you can build roads, right? And the way to separate these various fractions from each other is through fractional distillation. Now, natural gas is very similar. It's shorter. It's mostly methane, but there are some ethane, propane, and butane of it too. These latter ones are typically liquefied and are sold like that. For example, if you're grilling burgers in your backyard, chances are you can use, of course, charcoal, but you typically use propane. Now, coal, another important energy source, it's formed from the remains of plants that are buried under high pressure and high temperature over long periods of time. And so cellulose, which is, the most important plant material, that has carbon and hydrogen and oxygen. And then the ratio of hydrogen to oxygen happens to be the same as water. And so after these plants are died and buried, then the chemical changes gradually lower the water or oxygen and hydrogen content, and in the end it ends up being mostly just carbon. Now, depending on how much it is carbon versus other stuff, you have different qualities of coal, different maturation from lignite. Well, there's actually stuff before lignite too, like peat, which is used for whiskey making, okay, all the way to anthracite, which is the highest quality. And then each of these stages have a different carbon content, and the higher the carbon content, the cleaner it burns, and the most energy it packs. Anthracite is therefore the most valuable of these, and you can see the mass percentage of different element. And let me just draw your attention to that it's also always containing some sulfur, and so when you're burning coal, you have to take care of that, otherwise you're really polluting the atmosphere. Another source is remember where this is from? This power plant is in Springfield, right? So Simpsons. So what happens is that we can extract energy from the fission of radioactive nuclei, right, through controlled nuclear reactions, and so. The way it works is that if typically it says a uranium reactor, a uranium-235 gets hit with a neutron of a right energy, then it falls apart and then forms two smaller nuclei and a bunch of neutrons, and these bunch of neutrons will then hit other nuclei, and therefore you have a nuclear chain reaction. And if you control it properly, then you can gradually liberate this energy stored in the nuclei. And the way it works is that they produce steam, which is converted to mechanical work, and that is converted to electricity. And in 2014, which is a few years ago now, 11% of the world's electricity came from nuclear power. Also, there are a bunch of nuclear power naval vessels. Most notably, this looks like Nimitz class aircraft carrier. Is it Nimitz or Ford class? Anyway, so it's a nuclear aircraft carrier, and if you load it up with nuclear fuel, it can run for approximately 30 years. So the range is essentially unlimited. You don't have to refuel it like every 30 years. Okay. The attitude of different countries to this energy source is very different. So France, I think, is over 70% of energy is coming from nuclear. Therefore, they're not. They're pretty good from the global warming perspective, and on the other hand, Germany made a conscious decision now about decade or so ago to phase out all its nuclear reactors, and that was a response of the government to the demands by the Greens. Essentially, they wanted their vote share, and so they introduced this idea, which I think is a total disaster, because in the end, what it resulted is that you have to get the energy from somewhere, right? And if you're phasing out nuclear, there's not that much renewable energy available yet. So what this meant is that they shifted heavily towards coal. And so the fact of the matter is that if you're buying an electric car in Germany, then your global warming output is actually bigger than if you were to use, let's say, a diesel car, simply because the electricity that your car is running on, your electric car is running on, is simply coming from coal, right? And so you just have to be mindful of these little details, because for politicians, they're very good at lying and then quoting the misleading information, and so you have to really go into the science of it. Another important energy source that I like to talk about here, because of its size, is hydroelectricity. And essentially, it's electricity generated by hydropower. What happens is that through the gravitational force of flowing or falling water, you can generate lots of power, and this is the most widely form of renewable energy. Renewable means that you're not actually using up the water; it will be regenerated, and this is the Hoover Dam, of course, which is a terrific engineering feat. What happens is that the water flows down, and then as its gravitational energy decreases, that energy is used in the generator to produce electricity. Now, what is the problem with this? Is that only a few years ago, most of actual renewable power came from hydroelectric, and it's clean, it's nice and everything. But of course, you can see that if you're building something of this scale, then this would change the environment. And so, for example, when China was going heavily towards more hydropower, they destroyed entire villages. And then, of course, in a dictatorship, you can just do that, right? Tell people you're moving out. But in a democracy, that's much more difficult. And in fact, from the country I was originally from, in the late 80s, such a hydroelectric dam, the proposal of such a dam was one of the things that buried the communist regime, because they wanted to build such a hydroelectric power plant in one of the most beautiful sceneries along there in the river Danube, and a lot of people were demonstrating, right? And essentially, in the end, it brought down the regime, and of course, Ronald Reagan. Okay, so these are some important sources of energy, and then let me put in a couple of more relevant and renewable ones that we talk a lot about, and one of them is wind power, right? So what we're doing is we're converting the energy of wind into useful form by driving wind turbines, and a couple of years ago, it accounted to less than 5% of the world's electricity, but it's increasing big time. Now, of course, there's a lot of politics in here, and so certain states, for example, that bet heavily on solar, they intentionally try to kill wind power. California, of course, with its worst government known to mankind, is doing that. But of course, there are some problems with wind power too. These large-scale wind farms that are connected to central are pretty bad for birds, right? They kill a lot of birds. But for smaller turbines, you can provide electricity to even isolated locations where you simply cannot, take a long enough wire to get there. And wind power, there's a lot of it, right? There's a lot of wind. It's renewable. It's widely distributed. It's clean. And then furthermore, and then I'd like to draw your attention to this one, you can actually put it offshore, right? So, in fact, I think by most calculations, California has enough winds that we just offshore wind power, we can get all the energy we want. Of course, politics says something different. And of course, and then this is how I'd like to finish with, is just, again, to illustrate, science is usually more complicated than politicians present it to you. But, bioethanol, there was a lot of talk about that, and it's actually still mandated, especially, where we live. It can be used as a fuel. So essentially what you're doing is taking biologically produced feedstock, let's say corn or sugar cane, and then turn it into ethanol and distill the ethanol, which can be then used as a fuel, right? And then it's in certain places a certain amount of ethanol is mandated to be blended into gasoline. Most of the world's bioethanol production is in Brazil and the US, which I think this is an old data, but still a very large fraction. Now, in Brazil, at least, it makes some sense because it's much easier to produce ethanol from sugarcane, less energy is involved than from corn. But of course, when people present you ideas and how great this is, and it's all renewable and everything, is don't forget that this is coming from crops that are otherwise used to make food, right? And so it had effect on the global food supply. And so maybe about a decade ago, suddenly corn prices, maize prices just tripled. It also uses up arable land that otherwise would be used to produce food. And this is not even the worst part. The worst part is that it doesn't even make sense, because the energy balance of the ethanol production is actually, it uses a lot of energy. And so if you turn corn into bioethanol, it actually requires more energy to produce it than what you're getting out of it. And so you're, in the end, of course, depending on when you get the energy, but it's mostly fossil, right? So don't believe everything politicians say, but of course, there are some lobbies that are really powerful. But, sometimes it also comes down to ethical decisions, right? Whether you send the corn to people who are still dying of hunger in many places in the world, or whether to fill up the tank of this fat guy's SUV. Okay, so that was chapter 9. The calculations here are pretty involved in the concept too, so I very much recommend that after watching this video, go back to every single calculation and try to do those calculations. And after you've done the calculation, check your work whether we did it the same way. And then just a hint, I really like the Hess's law calculation, so there's going to be a fair number of those in the exam. So this was chapter 9, and the next chapter is going to be a continuation of thermodynamics when we go from energy to entropy. All right, so thank you for your attention.